covers modeling exponential growth and decay. So let's talk about exponential growth first. So this is P equals I. This is going to be the starting value right here. Let's say starting or initial value, starting value. So whether it's like the amount of bacteria, the amount of money, okay, the worth of a car. And then P is going to be the value afterwards, okay? So the value after a certain amount of time, okay? And T is, of course, the time. And you can write time in minutes or years or seconds, depending on the question. Now, for exponential growth, this one is going to be our growth, okay? And this is when B, which is like the base, so this is, okay, this is like the growth factor. So does it grow, like, does it double, which would be like a 2? Does it triple, which would be a 3? Does it increase by 30%, which would be 1.3? Okay, so this is the growth. And we're also going to take a look afterwards at the decay, and decay is if the base is between 0 and 1. So decay would be like a depreciation, okay? Or like if the bacteria was decaying because you're taking medicine for it. Okay, so let's take a look at actual examples. Okay, let's look at Salmonella growth. So Salmonella is a bacterium that causes food poisoning. Under favorable conditions, okay, so favorable conditions might be like heat, moisture, okay. One Salmonella bacterium will divide every 20 minutes to form 2, okay? So they divide and then they grow, okay, just like a normal cell. So suppose that there are 500 Salmonella to start with, and every 20 minutes the Salmonella doubles. Okay, so for example, for time 0, we start with 500, and then after 20 minutes it's doubled, so 1,000. And then another 20 minutes, it goes from 1,000 to 2,000. Then another 20 minutes, it goes to 4. And 4,000 doubles to 8,000. And 8,000 doubles to 10,000, or 16,000, sorry. Okay? And N would be 500, and this is pretty much like the equation. So the amount equals, well, we start with 500, and then we're going to double, so 2 is the base, and then every 20 minutes, so the time divided by 20. So whatever time divided by 20, and time is in minutes. Okay, expanded form, this is of course just 500. This is 500 times 2. This is 500 times 2 times 2. 500 times 2 times 2 times 2. 500 times 2 times 2 times 2 times 2. 500 times 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Yeah, because 500 doubled 5 times. So the exponential form, 500, 2 to the 0. 500, 2 to the 1. Okay, doubled once. 500 now doubles twice. 500 now doubles 3 times. 500 now doubles 4 times. 500 now doubles 5 times. Okay? So we can either do T over 20, or we can actually simply call T the number, let's go number of doubling periods. Okay, so let's just scroll down a little bit and we will plot this. So we know we start at here. Let's go 1, 2, 3, 4, 5, 6. So this is T, number of doubling periods. Okay, and this is going to be A, number or amount of Salmonella. Salmonella. Yep. And we have 1, 2, 3, 4, 5, 6, 8, 9, 10. So each of these is going to be So 2,000, 4,000, 6, 8, and 10. And I'm going to put amount of salmonella in thousands. Okay, so 1 in 500, I'm going to do this in another color. 1 in 500, 0 in 500, sorry. We got 1 in 1,000, 2 in 2,000, 3 in 4,000, 4 in 8,000, and we will stop there. And we do not have an arrow on this end because we can't go back in time. Okay, so we only have an arrow on the other end, and that's if the salmonella continuously grows. All right, so let's look at exponential decay. So radioactive waste. Radioactive waste from nuclear power industry has a half-life. So when we think of half-life, it's dividing by half. Okay, so this is like basically the opposite of doubling, of about 8 days. Okay, so every 8 days, 1/2 of iodine 131. This number doesn't actually mean anything. It's just like a title of the iodine. So you can even reread it like in your mind as 1/2 of the iodine decays to a non-radioactive form. So basically what we're looking at is like the amount of radioactive activity. So suppose that there are 500 grams of the iodine 131, to start with, and every 8 days it decays by half of its life. Okay, so number of grams of iodine, 500. After 8 days, there's only 250. After another 8 days, there's only 125. Okay, half of that is 62.5. Okay, 62.5. Another half of that is 31.25, and then one more half is 15.625. Okay, and how we found that was 500, and then 500 times 1/2. And then what we did for the 16, after 16 days, we times it by a half twice. And 24 days, we times it by a half 3 times. Okay, and I'm just going to go 1/2, 1/2, 1/2, and 1/2. Okay, and then I'm going to squeeze this in 500, 1/2, 2 halves, 3, 4, 5, and I'm going to squeeze just in down here. So we did 1, 2, 3, 4, 5 half-lives. Okay, exponential form, 500 times a half to the 0, 500 times a half to the 1, 500 times a half to the 2, 500 times a half to the 3, 500 times a half to the 4, and 500 times a half to the 5. Okay, very tedious. And I just scrolled down. So now let's go ahead and put the equation in exponential form. So the amount left is going to be 500 times a half t times, where t is going to be the number of half-lives. Half-lives? One of those. Okay. So I call it half-lives. So we're going to start at 0. So this is going to be 0, and then we're going to go across. All right. So we got 0, 1, 2, 3, and we went up to 5. So that's perfect. Okay. And the most we're going to have is 500. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each of these is going to be 500. 400, 3, 2, 1. Okay, and then T is going to be the number of half-lives. A is going to be the amount of iodine left. Okay, and we're going to go ahead and plot the 500, the 250, the 125. The 62.5, the 31, the 15, okay? Okay, so this is going to go as an arrow. Okay, so there's that. Horizontal asymptote by y equals 0 here, okay? And we're not going to put an arrow on this side because, of course, time starts at 0, so we can't go to the left of time, okay? So that is going to be exponential decay. We have a decreasing exponential graph. Okay, so now we're going to take a look at 4 different examples of word problems. I like personally creating equations and then just solving. Okay, so let's learn how to make equations. So example 3, the population of a certain country grows at an annual rate of 2%. So annual is like per year, of course. Okay, 2% is 0.02. If the current population is 3 million, so amount's going to be the 3 million. What will the population be in 10 years? So when we have a growth of like 2%, is actually 1.02 because 1 stands for like 100% of the current population and then another like 2% there. Okay, so since this is annually, we can just sub in that 10. Okay, so let's solve for what the population is going to be in 10 years. I get 3656. 983. Okay, and this you always want to round because population, you can't have 0.26 of a person. Oops, sorry. Okay, and now here's the second question. How long will it take for the population to reach 5 million? So we want the population to be, 5 million, and our equation is 3 million, 1.02, but we don't know the time. So let's actually solve for the time, okay? And this is going to be a little bit different than what we've seen. So we're going to divide each side by 3 million, so those go away. And basically we have 5/3. Let's see if that turns. Okay, let's just keep it as 5/3 because it's 1 2/3, I think. 5/3. Yeah, 1 2/3. Okay, 1.02 to the t. So in order to solve for 5/3, what we're going to have to do is we're going to have to change the base. So this might be a little bit new. What we're going to do is we're going to have 2 bases. So we're going to have 1.02 to the t, and we're going to have 1.02 to the something. So in your calculator, you have to put in 1.02, and you have to keep putting in different exponents until it equals 5/3, which is 1 2/3. So let's try 50. No, let's try 25. 1.02 to the 25 is 1.64. Let's try 26. Okay, so approximately this is going to be 26. Okay, so 1.02, if you put in your calculator 1.02 to the 26 is going to be approximately 5.3. So all we're really doing is rewriting this 5.3 a little bit differently. Okay? If we have the same base, we can drop the base. 26 equals t. So after 26 years, the population will reach 5 million. Okay, example 4. A certain radioactive element has an annual, per year, decay rate of 10%. So 10%, because it's decaying, it's actually decaying to 90% of what it was. Starting with 200 gram sample, so we know it's 200 grams, we're taking every single time 90% of what there's left. How many grams will be left after 3 years? Okay, so we just plug this in and solve. Okay, and I get 145.8. So after 3 years of having 90% of the 200, and then 90% of that, and then 90% of that, the answer is 145.8 grams. Okay, a type of bacteria has a very high exponential growth rate of 80% every hour. Okay, so 80%, but since its growth, instead of being 0.80 as that base, we're going to use 1.80. And this is every hour. If there are 10 bacteria, like to start with, so we can start by saying the amount is 10, and then we have our base. Okay, so again, this is the amount, this is the base, the growth or the decay rate. Determine how many, like bacteria, there will be in 5 hours. Okay, so every hour, since there's 5 hours, we're going to sub in that 5. Okay, for 1 day, what we're going to do is 1 day is how many hours? 24 hours. Okay, and then 1 week is going to be, well, we know it's 24 times 7 days, right? Of course, like 1 week. So let's solve that 24 times 7, 168 hours in a week. Okay, so let's actually just solve for it. So 10 is the start times 1.8, 80% growth to the 5, I get 188.9568. 188.9568. Okay, in 1 day, which is 24 hours, there are going to be 13382,588.45. Okay, that's a lot. Okay, and in a week, I don't even know if this will calculate it on the calculator because it's going to be so big. The calculator is going to give 7.68 times 10 to the power of 43. So there's actually like 43 decimal or 44 digits in here. So it's quite ugly. It's a very, very big number. Okay, let's do example 6. A species of an extremely rare deep water fish like rarely has children. Okay, if there are 281, so that's at the start, so that's our A. Okay, or our A naught, like our start, 821 of this type of fish, and their growth rate is 2% each month. So 1.02 because it's growth. Okay, 1.02 each month. Then how many will there be in half a year? So half a year is 6 months. Okay, because this is each month. Let's go 821, 10 years. So how many months are in 10 years? Well, there's 12 per year times 10. Okay, so there's going to be 120. I don't want to call it like doubling periods, but like 2% growth periods. Okay, and 821, 1.02, 100 years, so 1200. So let's put that in our calculators. Let's go 924. Oh, decimal 58. Okay, and 120. Let's go 8838.199. Okay. And if we got a 0 there, 1.7 times 10 to the 13. So there's 14 digits there. So that one's really long. Okay. So what's important about this is it's important to know that the amount is going to be the starting value. So, or I think we used I. It's going to be the base times the amount of doubling periods or half periods. Okay, half-life periods. So whatever that's measured in. But I think I gave you this in I. I usually use A naught, but that's what they teach more like toward university and college. Okay, like the amount at time 0. So we'll keep it at I.